And what I'd like to do now is just spend a little bit of time, it's basically algebra. It's just manipulating these expressions and then seeing how different specifications imply different types of spatial externalities, and particularly whether the spatial externalities pertain to the variables, the x's, or pertain to the unobservables, the error terms. And the second dimension is whether they are local, constrained in their spatial extent, or whether they are global, spread through the whole system. And we've already had a taste of this by looking at the moving average versus the autoregressive processes and looking at the covariance matrices that correspond to those. We saw that for the moving average process, the covariance in essence became 0 after the second neighbor, whereas for the autoregressive process, it just keeps going. The point of departure is to think of these models as structural forms and reduced forms. And this is really a counterpart, if you're familiar with simultaneous equations, it's the same way of thinking about things. So the structural form is actually what is supposed to come out of theory. And then the reduced form is when you put everything that is endogenous on one side and everything that is exogenous is on the other side. So the point of departure is this spatial structural form where you have, and we saw this at the very beginning yesterday as well, we have a vector of observations on y, which is somehow functionally related to that same vector of observations, but at different locations through this k function, the k of y function, and then in general some function of the x variables as well. So the value of y at a given location is a function of y at other locations, x at that and other locations, and the error at that and other locations. So it's a perfectly general way of thinking about this. This is not necessarily operational, it's conceptual. So then we solve it, and the solution is the reduced form. So the reduced form is something where we no longer have, the original specification, but we get all the y's on one side, and then the x's and the error terms on the other side. So this is a model that is actually can be used for policy simulation. See, the previous one we cannot use for policy simulation because of the simultaneity between the y, the dependent variable, and the spatial lag. We cannot take the neighbors as given when we're trying to model the full pattern, because in the full pattern the neighbors are unknown. Now in this form we can, because everything on the right hand side we know. I mean, we don't know the errors, but we do know that the errors are on average 0. So if we take a conditional mean, a conditional expectation, the errors for all practical purposes disappear from this, but the x's are still there. So we can do policy simulations, change the x's, and see what that does to the spatial pattern of the y's. Say this is a model for house prices, and some neighborhood improvement policies are in the x's. We can change these x's and see what this does to the prices of every single house in the data set. And then, of course, we can aggregate it any way we want. But the important aspect is that we can get this for every individual house. And we can spatially manipulate the policies. Because of this spatial system that ties everything together, we can see what happens, say, to the prices in neighborhood A if we do improvements in neighborhood B, not in neighborhood A. But because of the spatial multiplier, there will be an effect on the prices of neighborhood A as well. How strong? That depends. It depends on the connectedness structure, the weights matrix, and it depends on the value of the parameter. If rho is 0.9, it's going to be a lot stronger than if rho is 0.1. Okay? But this is how you can use this in policy experiments. So now what we can do is how we can analyze this in terms of a spatial multiplier. And as I mentioned, we're interested in two aspects of this. You know, the spatial range is one of them. That's the one we look at here. And then the other aspect is, what is actually the multiplier applied to? Is it applied to the observables, the x's, or to the unobservables, the error terms? And the local spatial multiplier, as we saw earlier today, is a moving average type of process where the spread is limited to whatever is specified in W, or maybe a second order, but that's it. It cuts off. The global multiplier is through this inverse that we approximate by this series expression, which gives us rounds and rounds and rounds of multiplier effects, not just of decreasing magnitude, but of spreading out range through the power of these spatial weights matrices. So then we can start our taxonomy, where we look at externalities in the error terms. These are, if you wish, unmodeled effects. For example, things like culture or sense of community, or those other things that we know are there, and we know they're spatially correlated, but we don't really know, we don't observe them. That's why they are in the error term. Or we can look at externalities in the actual variables, the covariates, and those are the ones we're particularly interested in for policy purposes. Those are the ones we can manipulate. And then in each of these, we can have them global or local, or we can have them together. We can have both externalities in the unobservables and in the covariates, and then again, local or global. So then we start playing our little algebra exercise, and we start with the errors. Local externalities are the moving average model in the error term. So if you estimate a moving average model for the errors, that implies local externalities in the unobservables. Okay. If you have global externalities in the unobservables, then the reduced form would have this inverse term here. If we work it out, what we end up with is what we thought we would end up with, a SAR error model. So this just kind of puts it in a different way, what we've seen so far a number of times already. The moving average is local, the autoregressive is global. Okay? These are both very familiar type models. Then things get a little less familiar and maybe a little bit surprising. We start with externalities in the covariates that are local. So externalities in the x's that are local, both the reduced and the structural form are the same when it's local. This is when we have our spatially lagged explanatory variable. So when we introduce, as the example we had earlier this morning, a variable that, for example, if we explain income by employment, local employment, as well as surrounding employment, the surrounding employment would be the WX. That implies a local form of externality. So if you change the employment in the neighboring county, it will affect my income. If you change the employment 2 counties away, it doesn't do anything for me. That's the difference. With the global model, we put the inverse matrix in front of the x's and work out the algebra. We end up with a spatial lag model, but not just a spatial lag model that has moving average error terms. So this is a SARMA model. So the global externalities in X only give us a lag model, but a lag model with moving average error terms. So these are the kinds of implications. The reason this came up, actually, the reason I started thinking about this is, several years ago when I did a class like this, there was one student in the class who didn't like the particular structures that followed from, say, the standard lag model and the standard error model. And he kept insisting, well, there are other combinations. I want a model where these multiplier effects do not apply to the error term, but only to the x. Now, what does that do? And it takes a little bit of algebra, and this is what it does. It gives you a spatial lag model. The spatial lag model as is gives you the double whammy, as we already saw. It gives you the global multiplier for the x and for the error term. But this one is different. It constrains, if you wish, the multiplier effect only to the covariates and not to the unobservables. Now, I've never used a model like this, but there are people who have, and there are substantive contexts where this is what you want. And so what I wanted to do with, this is a paper, what I wanted to do is to show what are the implications for your model specification of particular types of externalities that you desire from a substantive point of view, from your model point of view. And then the last one, this is the fun one, is where we throw it all together and we have externalities both in the errors and in the x. And as you might expect, the local one is straightforward. It's moving average errors with a spatially lagged explanatory variable. So this is, remember a few minutes ago, I mentioned that there might be identification problems if we have a SAR error with a WX. But here, there is no identification problem because we have an MA error with a WX. So if you have the moving average, it keeps it local, and that localness keeps it from interfering with the interpretation of the other variables. Whereas below, we have both global models, and here we see something very interesting, namely the model that we usually focus on, the mixed regressive spatial autoregressive model, actually imposes a constraint on the nature of the externalities. The constraint is that the externalities in the x and the externalities in the error term follow the same process. Now, is that reasonable? Maybe, maybe not. If you want them to follow a different process, so if we let the rho be different from the lambda, we get this monster here. And here, as you can see, you will have all kinds of identification issues to keep the effect of the rho and the lambda separate. So that is actually more of a conceptual model rather than a practical model. In practice, it will be very difficult to tease out the difference, what exactly is rho and what exactly is lambda. And you can do it if your data is rich enough. As always, if the data is rich enough, you can fit more complex models to it, but if the data is not rich enough, this is not going to work. And in practice, and even though conceptually this model is perfectly okay, in practice you tend to run in all kinds of problems trying to even get this to converge. Because what happens, anytime you have this situation, the sum and the product, the computer program doesn't know which is rho and which is lambda, and they can flip them around. And if you're not careful in the estimation process, what happens is that you see one going down, the other one going up, and then it bounces back. The other one goes up, and the first one goes up again. And if you keep doing this, then you see that, in fact, it keeps going up and down. Now, if you're not careful, and you just take the defaults, and your program finishes after 20 iterations, it gives you two numbers. But those are just the numbers where it happens to be in the bouncing process at iteration number 20. So you have to be very careful with these models. They can be estimated, but it's very tricky. And I've actually seen situations where this bouncing went on for 24 hours, and then we finally said, this is enough, this is not going to work.
Can you elaborate a little bit more on the local model cross-regressive with the SAR error? You were saying an identification problem. Is there any way around that?
The identification problem, there really is nothing to do about that because you are imposing a complexity that the data are not able to disentangle. So the only way to disentangle that is to put other structure in it. And one way you can get at it is, for example, it's through the x variables. Because the x variables give you a handle remember there is this lambda wx in there, and beta. So the lambda times the beta, you get the beta estimate, then you get the product of the beta and the lambda. And if the specification is correct, you have k of these. So for every beta, say you have 5 covariates, there are 5 constraints that says that beta and then lambda beta, this lambda has to be the same lambda in each of these situations. So you have 5 constraints. Out of these 5 constraints, you could extract a lambda value that you can then use in the, but that's where you get in trouble, in the lambda plus rho or the lambda times rho, you could use to extract the rho. But which one you extract, that again is not straightforward. So if you do a fully nonlinear estimation and there is enough rich variability in on the x side, you can actually estimate this. But if there's not, forget it. And I've just seen too many cases where it does not work. And it's very important, and I will reiterate this many times, that it's not because you get a number out of a computer program that that is a proper estimate. You know, your computer program doesn't care. It just runs and spits out numbers. But if the likelihood is not correct to begin with, this is not a likelihood, a maximum likelihood estimate. And similarly, if this is a process that is not converging but just bouncing back and forth, and you just arbitrarily cut it off at one point, you get numbers. But these are not proper estimates. So that's something to be very wary of. These, to estimate these models, it's actually fairly complex. And some of the programs are basically black boxes, and you don't always know why they stop where they stop and what is going on inside the black box. So you have to be very careful as the models get more complex to make sure that the data can actually support this model. So personally, I'm not a big fan of these higher order models. My typical advice is, if you find, and we may find this in the lab tomorrow, say you estimate a model with a spatial lag, and you do a specification test, and you find that the errors are still spatially correlated. Now, the natural reflex is to then estimate a model, a SAR-SAR model, and to progress in that direction. What I tend to favor is to revisit the original model and maybe use a different weights matrix or use a different specification and see if you can't eliminate the problem that way. And in my experience, that's by far the easier way to eliminate the problem than to go to these higher order models. Another alternative, and one which we won't cover here, but we will in the Frontiers course, is back to these autocorrelation consistent covariance matrix. And so there, the approach is you estimate a spatial lag model, but then you construct a covariance matrix for the estimates that is based on a generic possible dependence structure, which is essentially a non-parametric approach. So you don't impose a structural form, which means you don't have to worry about identification because there's no functional form. You just estimate the whole thing as a generalization, if you wish, of the White approach for heteroscedasticity. But that work is still in its infancy. Actually, the paper hasn't even come out yet. It's been around as a working paper for a while, and we have implemented it in our software, but this has not been used very much, and the properties are still not fully understood as to what are the trade-offs involved. And this is something we'll see tomorrow. In all of this business, there are trade-offs. Let me give you the example of spatially correlated error terms. The OLS, ordinary least squares estimation, is still unbiased. That's a good thing. We know the standard error, if we just naively take our printout as it is wrong. How wrong? That's the bottom line question. And it's important because the alternative, which is what we'll see tomorrow, is to use, say, a maximum likelihood procedure, which doesn't have finite sample properties, but has properties based on the limit. And so in which situation, and you know, there's often a misconception about this, because an estimator is consistent, meaning that in the limit it approaches the correct value, that doesn't mean it's unbiased. So in your actual data set, you don't know, without doing a lot of simulations, you don't know how good this consistent estimator is. And in fact, it's a bias variance trade-off. You may very well end up with a slightly biased estimator but a smaller variance, whereas your OLS is unbiased but has a larger variance. And so in this trade-off, where is the tipping point, so to speak? And that is still, in unlike time series where there's, you know, literally hundreds of papers doing simulation exercises, in the spatial domain it's much more limited, and there is a little bit of a sense of what is going on, but nothing near as comprehensive as you have, say, in the mainstream econometric literature. So this is something to keep in mind, and I had some conversations with a number of you already where your data sets were fairly small, and in those cases the methods that we will discuss tomorrow are really not very reliable, and you may be better off using OLS and then some kind of adjustment to the standard error, where at least you have the unbiasedness. All the other methods are of course superior in large samples, but how well they do in small samples is still very much a matter of research. So this is where I wanted to stop it today. We'll now move to the lab. We can take a short break and then move to the lab.